Bismillahirrahmanirrahim. Welcome back to my channel. This video is going to demystify a very important concept, which is a very important concept and a core concept to understanding software-defined radio and digital signal processing. And this concept has been generally known as sampling. What's sampling basically? So we're going to look at in this video, I'm going to show you what sampling is. If I don't fulfill the Nyquist criteria, what will happen to my signal? If I fulfill the criteria, what happened to my signal? And I'm going to show you that actual representation using a software-defined radio platform like HEC-RF. And what do you mean by sampling when it comes to software-defined radio? Let's just basically first understand what sampling is. Briefly, we're going to look at the demo, and then I'm going to on GNU Radio using this flow graph, and then we're going to also look at it, the effect of sampling when you're using a software-defined radio platform like HEC-RF or RTLSDR dongle. But I'm going to demonstrate using HEC-RF because I can go from 1 mega samples, I can and go up to like 20 mega samples or something like that, up to 20 mega samples. So the criteria is quite simple. We have something called a Nyquist theorem, and Nyquist theorem says that if you have, hold on a second. So this is what Nyquist theorem is. So the thing about Nyquist theorem is that the first thing that you encounter when you're dealing with any type of digital processing, signal processing, is actually the first core idea is actually sampling. And sampling is basically part of your chip, which is your ADC. So whenever you have a signal that is in a form of an analog signal, it needs to be converted for pre-processing or post-processing using something called an ADC, analog to digital converter. And the first step that an ADC does, it converts that analog signal, which is, let's say, my voice right now, that is going into my speaker through my mic to my laptop. It samples that into a discrete signal, which is called digital signal. And sampling is the first thing that it does. It takes a smaller snapshot of your signal. So the Nyquist criteria says that your frequency, that your sampling frequency should be twice or greater than your fundamental frequency, or your frequency, the desired frequency you want. So it should be greater than or equal to twice of that frequency. That's what a Nyquist criteria says. This is just defining the proof. Let me give you a better version. This is a lot of math there. So what is Nyquist theorem? So it should be a periodic signal must be sampled at more than twice the highest frequency component of your signal. So the Nyquist criteria is twice of whatever your highest frequency is that is there in your signal. You should sample, your sample rate should be selected based on that. So in order for me to actually show you this, let's look at this. So I have a signal source that has different sample rate. So let me open up the signal source. The signal source can be a waveform, and this waveform is being depicted by this GUI chooser, where I'm choosing cosine, square wave, triangular wave with different codes: 102 for cosine, 103 for sine and square, and 104 for triangle. And I'm choosing a frequency which is being controlled by this GUI range. I'm going from all the way from negative 10 kilohertz all the way up to 10 kilohertz. And amplitude doesn't matter. It does, but it doesn't matter generally. 0.5. And I also have a sample rate. Sample rate is actually underlined, which means anything that is underlined in GNU Radio, it can be controlled using a block called a chooser block or a range block. So right now I'm choosing a chooser block to change the sample rate from all the way from 8 kilohertz all the way up to 32 kilohertz samples. That is going into a throttle block, and then I'm visualizing the signal in time sync, and also I'm visualizing the same thing in my frequency sync. You got to remember, this sampling is being done. The component that performs sampling is actually your ADC, and this is the first step in ADC. If you have a proper ADC and proper sample rate, you will be able to reconstruct your signal again from those discrete samples after digitizing that signal using ADC. So let me run this flow graph and show you. Let's wait for it. So right now we're looking at a cosinusoidal signal because there's frequency 0, that's why you're not seeing anything. It's just some DC component at 0. So let me increase this frequency to 1 kilohertz, and I should start seeing a 1 kilohertz of cosinusoidal signal. So the sample rate is what, 8? So I would see 8 samples. So starting from here, so this is this is your cosinusoidal signal. I should see 8 points. 1, 2, 3, 4, 5, 6, 7, 8 points. So 8 points are there. If you do 16, you will see 16 points. Definitely this is much better representation of your signal. If you were to just if you were to reconstruct your signal based on just these sample values, this is a good reconstruction of your signal as compared to your 8 kilohertz signal that has points which are further apart. Now, having a sample rate of 32 kilohertz, which means this is much better reconstruction. If you were to just giving me these points, every single point on X and Y axis, if I were to plot these points, then the more the points are, the closer the representation of the signal is going to be. So this is what sampling is all about. Now, if you're looking at this signal at 1 kilohertz, let's go back to 8 kilohertz, and you have a signal source of 1 kilohertz, which is good. So the sampling rate should be what? Twice of whatever your actual periodic signal frequency or whatever your signal frequency is. So right now it's 1. So I've chosen this sample rate to be 8 kilohertz. This is good enough, and I'm seeing this at 1 kilohertz. Let me just increase this signal, because due to processing, it takes a lot of processing. That's why you should see a peak like this. This is just due to the processing power. So let's say I've chosen this to be 2 kilohertz, and you're still seeing some signal, and I should see this spectrum to be moved at 2 kilohertz. So far so good, because twice of 2 is 4 kilohertz, and our sample rate is chosen to be 8 kilohertz, which is good enough. Let me choose this to be 3 kilohertz. Nyquist criteria says 2 times of this frequency, which is 6 kilohertz. If my sample rate was 6, this is good enough, and I'm still seeing this on my frequency sync, so which is good. Let me choose this to be 4 kilohertz. Now it's basically fulfilling the minimum criteria. Actually, 2 times is actually the minimum criteria. That's the minimum you should select. I'm still seeing a signal at 4 kilohertz, which is good enough. Now, this is what happens if you don't sample your signal correctly. So right now, this is the minimum criteria that you're meeting. We're trying to meet. We are meeting right now, which is the Nyquist minimum criteria twice, which is 8 kilohertz. So 4 kilohertz of signal, twice of that is 8 kilohertz. 4 kilohertz of signal, yeah, it is there in the spectrum and so on, but this is still not a good representation of my signal. Now let me change this to 5 kilohertz. Now what will happen when I change this to 5 kilohertz? My sample rate is 8 kilohertz. It's not fulfilling the Nyquist criteria, because twice of that should be at least 10 kilohertz. Now, whatever the signal that you start seeing on your spectrum definitely is not at 10 kilohertz. It's somewhere around 3 kilohertz. This is called aliasing, because you're seeing an alias of that signal. Your actual signal is 5 kilohertz, but on your spectrum, you're seeing totally a different signal. Why? Because you are not fulfilling the criteria. This should be at least 10 kilohertz. And in order for you to figure out how much this aliasing frequency is going to be, the definition is quite simple. Whatever your sample rate is, subtract that from whatever your signal frequency is. So if your sample rate is 8 kilohertz, your frequency is 5 kilohertz. So 8 minus 5, 3 kilohertz. This is going to be your alias frequency. Aliasing frequency is 3 kilohertz. Now, if I change the sample rate to 16 kilohertz, I'm good to go. I don't need to worry about anything. Why? Because I'm fulfilling the criteria and I'm seeing my signal at 5 kilohertz. Now, if I were to increase this, let's say to 8 kilohertz, I am fulfilling the minimum criteria. Minimum criteria. I am still fulfilling the minimum criteria, but look at this. If I increase this to 9 kilohertz, now I start seeing alias frequency. Now I would start seeing the frequency which is not 9 kilohertz, it's totally something else. Now what is this frequency? This is around 7 kilohertz. Why? Because 16 minus 9 will give you 7 kilohertz. This is your aliasing frequency. also, sampling allows you to visualize an entire spectrum. I will also show you this. Look at this. Your sample rate is 16 kilohertz, which means from positive you can go all the way from 0 to 8 kilohertz. And then on your negative frequency, you will go from 0 to negative 8 kilohertz. So if you were to look at the entire spectrum going from a negative 8 to 8, this is actually 16 kilohertz. 8 plus 8 is 16 kilohertz. So on your left side, on your right hand side, you can go up to 8 and 8 and total of 16 kilohertz. Basically, sampling also does what is the chunk of frequency you can seed at once. All right, keeping that in mind, let me just, I have my HackRF is plugged in. Let me turn this off and let me open up my GQRX, which is running in the background. Right now I have, whoa, what happened here? Okay, let me just run GQRX again. Now when I open up my GQRX, I have HackRF which is connected. Wait for it. All right, the first thing that it asks me, okay, whatever. The first thing that it will ask me is this. So I am visualizing, let's go here. So I have chosen this to be HackRF. I can change this rate to anything I want. So right now I've chosen 1000 kilosamples or 1 mega samples per second. Let me click OK and let me hit play. So this is the actual hardware that I'm looking at. So what I'm visualizing right now is actually a signal that is going from 936. If you can focus it here, it's going from 936. I cannot move it here because this will actually change. I will be able to change the span. That's why. So I'm going all the way from 936. Believe you me, that is starting from 936 and all the way up till here 937. So 936, 937, because of my sample rate, I am also visualizing the spectrum that is 1 mega samples. Now I can go in and I can choose this to be 8 mega samples. This is the sample rate that I have chosen. Let me just click OK. Now what is it that I'm seeing? I'm seeing all the way from 933 megahertz if you were to focus here, and all the way at the end of the spectrum, which is 940, 96, which is 941. So I'm looking at what? 933 all the way up to 941 megahertz. So I'm looking at about 8 megahertz, 8 mega samples. It also allows me to actually manipulate my bandwidth as well. So also, if I change this to, let's say, 20, which is the supported sample rate for HackRF, I hope so I'll be able to see 20. So right now I'm starting at 927 and I am looking at the spectrum that is going all the way up to 947. So this allows me to actually visualize my spectrum as well. So generally your RTL SDR dongle, the cheaper ones have sample rate of about 1.8, but the higher version like the V4 RTL SDR, that has sample rate of about 2.4 mega samples per second. Also remember this. Yes, you can oversample your signal, that's not a problem, but the problem is it actually requires a lot of computation power. So you gotta have, you should think of a trade-off between what is it that you want to select and what is it that you don't want to select based on what type of a signal that you're working with. So that is quite important. Just to give you some few numbers, for example, AM, you can choose sample rate up to like 250 samples per second, 250 kilo samples per second, because generally they are in a range of about their bandwidth is about from 3 to 12 kilohertz. So whatever the maximum frequency is, you will choose the sample rate accordingly. Just like for FM radio, the entire bandwidth of your signal is 20 mega samples, but individual channel is about 200 kilohertz. So if you're just focusing on a single channel, you can choose like 1 mega samples per second, 5 mega samples or 5 megahertz or 5 mega samples per second for GSM, and ADS-B 2.4. Wi-Fi, you have 20 mega samples because the entire band is about 20 mega samples. So it depends on application. So sample rate is very, very important because you want to avoid this aliasing problem. If you don't do that, you will have a signal that was not supposed to be there and it's there. So I hope you find this video to be helpful. You understood the concept behind sampling rate and DSP and software defined radio. So I hope you like the small video. Thanks for watching, and don't forget to like and subscribe to my channel.